the compound with molecular formula C9-H10-O that gives the following IR and H-Nmr spectra. The first place to start here would be to finding the degree of unsaturation for this compound. So let's get started. So there are totally 9 carbons, so 2 times of 9 plus 2. There are no nitrogens in this compound, so it's going to be 0. And number of halogens is also going to be equivalent to 0. And the total number of hydrogens in this compound is 10. So that's divided by 2. So it's going to be 18 plus 2 minus 10 divided by 2. So it's going to be 20 minus 10 divided by 2. So the total number of unsaturation here, the degree of unsaturation here is 5. So which means it could be a mixture of double bond, triple bond, or even aromatic rings. Okay, now let's see whether we can get some details from the IR spectrum. So in the IR spectrum, we could definitely see that there is a carbonyl stretch. The carbonyl stretch is right there, and it comes around 1700 centimeter inverse. Okay, and when you draw a line around 3000, you can see peaks on either side of 3000. Okay, these peaks are going to correspond for, these absorption bands are going to correspond for the sp3 carbon hydrogen stretch, and it's going to correspond for sp2 carbon hydrogen stretch. And apart from that, there is a peak around 1600, and this is going to correspond for the carbon-carbon double bond in the benzene ring. Right, and the peak around 1500. Okay, all this is going to tell that we have a benzene ring. Okay, let's find out. Let's write down. We have a benzene ring, and we have C double bond O, and that definitely corresponds to a total of 5 degrees of unsaturation, because there are totally 3 double bonds in the benzene ring, and the ring itself is going to count for the 4th degree of unsaturation, and for the 5th degree of unsaturation we have C double bond. So these are the information that we could get from the IR. Okay, now let's look into the NMR spectrum and see what information we can get from there. As soon as I look into the NMR spectrum, I could see there are some peaks in the aromatic region, and these peaks are well separated from each other, and they account for a total of 5 hydrogen. And this is consistent with the mono-substituted benzene ring, which has a strong electron withdrawing group on it, because the peaks are shifted farther downfield and they are separated well. Okay, and when I look into this region right here, I have quartet. So I have a quartet, and I also have a triplet. So this is consistent with an ethyl group. Okay. Now we already have some idea about the compound, but it's always best to do this complete this table. Okay, so let's fill this one up. So we have one peak right here. Okay, it's about like 1.2 ppm. So let's write it down, 1.2 ppm. And the total number of protons here is 3 hydrogens. So 3 hydrogens. The multiplicity for this is triplet. So which tells us the total number of neighboring protons that this proton experiences is 2. Right? So normally when you consider a methyl protons, it could account for the total of 3 protons, but they're normally going to come around 0.9 ppm, right? But here we can assume that these are still methyl protons, but they are connected to an electron withdrawing atom or group. Okay, so which means, and that is the reason that they could be slightly downfield, right? So this should be for methyl protons, and when they are adjacent to a methylene groups, that's when it's going to be existing as a triplet. So this signal right here at 1.2 is going to correspond to the CH3 protons. Now let's go on to the next peak. The next peak right here is going to be, is at about like 2.9 ppm, and it corresponds to 2 hydrogens, and it is split as a quartet, which can be seen right here, 1, 2, 3, 4. So it's split as a quartet, and the total number of neighboring protons, we can assume it to be 3 hydrogens, right? And it is definitely consistent with this methylene proton, right? So this methylene proton will be split as a quartet because of the 3 methyl protons. Okay. So the peak at 2.9 ppm is going to correspond to the methylene protons. So normally when you have a pattern like this, it is definitely going to be consistent for the ethyl group. So together it's going to give a triplet and a quartet. Now the last thing here is the aromatic protons. There are a total of 5 hydrogens, and we have already concluded that this is going to be a monosubstituted benzene ring, where the peaks are well separated from each other. So the peaks are existing from 7.4 ppm to about 8 ppm, and there are 5 hydrogens, and let's just put multiple it. And this is going to correspond to something that's going to be connected to an electron withdrawing group. Okay, now let's put all of these information together that we have got from IR spectrum, NMR spectrum, and the degree of unsaturation. So from the IR spectrum, it was very clear we have the C double bond O and also the benzene ring. And from the NMR spectrum, it was clear that that benzene ring is connected to an electron withdrawing group, and also it has an ethyl group, right? So let's put everything together and account for the total number of carbons, hydrogens, and oxygen in the compound. So we already know that there is a benzene ring which has a substitution on it. Okay, for the normal benzene ring, it's going to be, for the unsubstituted benzene ring, it's going to be C6H6. For the monosubstituted, it's going to be C6H5. And we already know that there is a carbonyl group. So we are going to add 1 carbon and 1 oxygen. And then we know that there is an ethyl group. The ethyl group is going to correspond to 2 carbons and 5 hydrogens. So on the whole, if you calculate the total number of carbons, hydrogens, and oxygen, it is going to be C9-H10-O, which is definitely the same as what we have been. Okay, now the final thing that we have to do is put all of these 3 parts together. We have a benzene ring, we have a carbonyl group, we have a CH2CH3, right? The fact that the CH2CH3 groups are like slightly shifted downfield, and also there is well separation of the different peaks in the aromatic region, tells us that the benzene ring is connected to a carbonyl group, and also the CH2CH3 group is connected to a carbonyl group. So the best way to arrange these 3 different parts is when the carbonyl group is sandwiched between the benzene ring and the ethyl group. So it's going to give us a ketone. So this is going to be the structure for a final compound, for the compound which has the molecular formula C9H10O, which has these 2, which exhibit these 2 spectra.